Alright, so moving forward, we're going to look at part 3 of the Project 4 um, content. And this is going to be to design and implement a fourth order bandpass filter by cascading first order RC filters. So, let's look at the theory real quick. So we start off with the typical RC low pass filter and RC high pass filter. You can derive the transfer function for these by just doing the voltage divider expression, and then wherever you have the derivative part that you get from the capacitor, you just switch to S, and then you just rearrange to this form here, which is what we get, and we also do the substitution 1 over RC equals omega C. So there's that. And we can see the derivation for the high pass filter transfer function here as well. And whenever we implement this in MATLAB, we will also perform the substitution to get from regular frequency to angular frequency. So we start, just like before with for impulse invariance, we start by just going into the time domain by using the inverse Laplace transform pairs. This is pretty easy for these filters because they are first order filters and they're very simple. We have a nice pair right here. It is omega c times the exponential of negative omega c times t, and then we bring it to the discrete time domain by doing the substitution t equals nts, which you can see here. There's a t there, there's our nts, and then we do the substitution alpha equals e to the minus omega c times ts, just to make this look more like a z-transform pair. So in the z-transforms, alpha to the n times u of n is just 1 over 1 minus alpha times z inverse. And then we have just the omega c out front, which, because of linearity, can just be left there and then multiplied into the z domain transfer function. So there you go, right here. And then for the high pass filter, the story is pretty much the same. The only difference being we now have an s in the numerator of our transfer function, and so we pull that s out front, and then whenever we do the inverse Laplace transform, just like with one of the parts of our notch filter, this becomes a derivative with respect to time, so we have to perform the product rule for derivatives, and we end up with the Dirac delta yet again. Just like in the other expression, this Dirac delta we end up evaluating this exponential at t equals 0, and so it just basically goes to 1, and then when we perform the substitution t equals nts, we end up dividing by ts to get the delta n right here. So then at that point we have this expression right here. We also did the substitution for alpha, so that's just like before. And then we just performed the inverse z transform, the forward z transform, and we get this expression right here after all the algebra and stuff. All right, and real quick, we'll just go over the bilinear stuff as well because it's pretty simple. You perform the substitution. S equals 2 times fs times the quantity of 1 minus z inverse over 1 plus z inverse. And then you just algebra yourself to this version right here. And just like you'll see, and just like you've seen in the notch filter example, we end up dividing this whole thing, numerator and denominator. We end up dividing it by the value right here, which is the first denominator coefficient, and that way our first denominator coefficient becomes 1. And that just makes it easier whenever running it on the DSP board. You don't have to divide everything by that later. You can just divide it right now. So then we have the high pass filter version, and same story. And just like before, we multiply top and bottom by z, 1 plus z inverse to get rid of the nasty fractions within fractions, and then we just algebra everything together, and we get this. All right, so let's look at the MATLAB stuff. So we have our F domain set up here. We have our sampling frequency. We have our high cut, which is going to be the cutoff frequency for the low pass filter, and then we have our low cut, which is going to be our cutoff frequency for the high pass filter. So it's sort of backwards. We set up our frequency range, and then we call these functions to create those low pass filters and high pass filters by passing them the sampling frequency and the cutoff frequency for each of them. So here for like the low pass filters, we send it the high cut, and for the high pass filters, we send it the low cut. So we can look at those functions down here. So here we have, this is the omega c in the numerator, and then it'll be omega c over 1 minus alpha times the inverse. So that's why you get that there. And then we do some gain scaling. Without this, our impulse invariance form is above 1. It's like 2-ish. But anyway, it's at 0 dB when we do this, which is important. So, but we don't have to actually do that on the high pass filter for some reason. And as you mentioned in the notes, doing the impulse invariance derivation for the high pass filter doesn't seem to work out very well, or it's frowned upon or something. I didn't notice any initial problems with it. I did have to multiply by TS here, and I'm not exactly sure why that is, but we have it there anyway. And so then we move on to the bilinear here. Same story. It's just like what we had derived right there. Omega C 2 plus 2fs plus omega c and minus 2fs plus omega c. Right there. And then we go ahead and divide by that first denominator coefficient, like I mentioned. And then same thing for the high-pass filter. So let's go ahead and test the impulse invariance form. If you've been hearing white noise in the background, I actually have it running right now, but I'm going to reload it, of course, just for authenticity. So we have a low cut of 100 hertz and a high cut of 3000 hertz and a sampling frequency of 96,000 hertz. And we are generating the coefficients for the impulse invariance filter, which happens right here. So we grab the low pass filter coefficients and the high pass filter coefficients there and there, and we plot their responses here. Then we do multiple convolutions to simulate essentially getting our fourth order filter. Not simulate, but actually get the fourth order filter. So this is like multiplying. It's actually polynomial multiplication, since our B and A are the coefficients of the polynomial. It's just multiplying them isn't the same as multiplying the transfer functions, whereas convolution will make it the same as doing that. So then we also plot those, and then we generate the bandpass filters by convolving the coefficients for the low pass and high pass here and here. So we get just a regular B sub double I, and that's what we're throwing into the coefficient file over here. So let's look at some of what we get here. So this is the low pass filter, single order low pass filter impulse invariance response. And since our high cut was 3000 hertz at negative 3 dB, let's see, 3000, that's 1000, 2000, 3000 should be right there ish. Yeah, perfect. And then we also have the high pass filter impulse invariance. So if you look at this, it looks good. And if we go to, I think it was 100 hertz, it should be right there. Should be about negative 3 dB as well. Then when we go to the fourth order, it'll now be negative 12 dB instead of negative 3, since we have a fourth order filter. It's 4 times the amount of attenuation. So since the attenuation was 3, 4 times 3 is 12. So there we go. There's our high cut, and our low cut is going to be right about here. Yep, pretty close. Then I went ahead and also created a zero pole plot for our filter. I believe this is actually the wrong one. Yeah, that's for the bilinear transform. Let me change that to the impulse invariance one real quick. Everything come back. There we go. And if we zoom in here, we can see that the poles are inside the unit circle. So we are stable, technically. And if we go ahead and look at the resulting bandpass filter, I plot the bilinear transform and impulse invariance response together. The impulse invariance response is in blue, and you can tell by your inability to see it, necessarily, that it is behind the orange, or behind the bilinear transform. They're pretty much the same here. And so, looking at our cutoff frequencies again, they won't be at negative 3 dB, they'll be at negative 12, which is right there, and you can see that it's at 100 and 3000. And in our passband, we're actually still attenuating, because in order for this method of bandpass filter generation to work out well, the passband frequencies have to overlap. And if you look at our low pass and high pass filters for the fourth orders, you can see that we don't get unity gain until like well further back, if we're talking about the high cut, further back from the cutoff frequency, or further above the cutoff frequency. See, where our cutoff frequency is at 3000 here. We won't get unity gain until really about here. It's like 300, so it's like an order of 10 less. And so if we look at the bandpass filter, the highest gain we're getting is about negative 1 dB, so not great. Not a great bandpass filter, but it's a bandpass filter regardless. And also, I went ahead and took the opportunity to create a simulation function, which essentially just runs the same way that it does on the DSP board. I'm going to go ahead and make sure that I'm simulating the impulse invariance filter, and if we run it, we're able to see that this is our input signal here, and then this is the output signal. So it starts out high, but then quickly attenuates, and like I mentioned, or I haven't actually mentioned this quite yet, but our test signal is at about 60 hertz, and if we look at our BPF, 60 is going to be right about there. There? Yes. A negative 22 dB. So it's not actually going to drive it all the way to 0, though negative 22 dB is pretty big. We're still going to get some coming through here. And anyway, okay. So I went ahead and have these coefficients loaded. I'm going to program them onto the DSP board over here. And we're just going to observe the results. So, if we go ahead and look at our, I think this is going to be the right one, because we're running the Gaussian noise through, and I have this spectrum scaling it so that it gets rid of that Gaussian nature, and we can see what it's really attenuating here. And it's kind of hard to tell, because we are getting some extra stuff down here, and this is because of the high-pass filter. a high-pass filter is a little bit finicky, like you mentioned, and with this showing up, I think that might be what that is. I ran this with just a high-pass filter before, and I had those lower frequencies coming in. If I go ahead and instead of running the Gaussian noise, I just run like a song, we'll be able to see that. This one again. Keep all your secrets locked up in your heart safe. So it doesn't sound like a full volumes sound you get from a song, and thankfully that tells us that our bandpass filter is actually working pretty well. Now, it's working for the impulse invariance technique, but I've been having significant trouble with the bilinear transform, and I'm not completely sure why. There will be a separate video in Code Composer showing the errors that I'm getting. Essentially, I think it's some sort of rounding issue, and we're getting nan values in our output buffer, or not a number, which tells me that some of the values that we're calculating are blowing up to infinity and then being multiplied by like 0 or something, like one of these zeros here. And 0 times infinity gets you nan in the floating point representation of data. So that's why we're getting nans there, is if our filter is rounding off something too much, and then that rounding error causes instability, then we end up with not a number. So if we just take a look here, I'm going to make sure that there's no obvious errors. Yeah. Those all look good. And you'll see in the simulation that I have that this actually does work. So we're going to change a lot of things here. We're going to make sure we're loading the bilinear transform coefficients. We're going to simulate the bilinear transform coefficients. And our 0 pole plot is going to be bilinear transform. So, with that said, let's go ahead and... Oh, by the way, the simulation is running at a... the simulation is simulating a signal at 60 hertz, so it's within the stop band. So there's a simulation. You can see it's being attenuated significantly. Again, it's just outside the stop band, so it's not being attenuated that much, but yeah. If you look at the 0 pole plot, we'll see our poles are inside. If we look at these are more important. So yeah, poles are inside the unit circle. And like I showed you, the simulation is attenuating, so it should work. Here's our new coefficients. They're great, but they're useless. So I'll show you that. It actually won't be much to show you in this video, but in the other video that I will upload, I'll title it like bilinear transform RC filter problems or something. I'll include that for you to look at. Initially in that video, the impulse invariance response also wasn't working, but suddenly started working. So, and I've shown it working here too. Anyway, let's go ahead and, yes, we're going to load up these new coefficients. And we're going to let it run. And if we go here into the digital audio workstation, you can see we're not getting anything. And I can see here in Code Composer that our output buffer has now been filled. If I stop it real quick, our output buffer is filled with nans. So, I've done extensive bug testing and looking into why this might happen, and I cannot for the life of me figure out why. I can go ahead and show you that at least the single order filters are working. If I bring the sampling frequency way down, and I go ahead and just get these out of here, we're going to load up. So that cascade part right there, that removes them from being fourth order filters. So now they're single order. And you can see here that single order filters are much weaker, and we have essentially like half the remaining signal. And here's what it looks like. So we're doing the bilinear transform. Our test signal is at 2, 3, 4, 5, 6 kilohertz. 60 hertz. And you can see it's at about -5 dB, which isn't very correct. I think it might be there. Why is it there? That is so bizarre. Let's look at. Yes. So 60, right about there. That's why. Oh yeah, because this should be at -3 dB. Yes. Okay. Sorry. That's normal. Okay. Again, looking at the pole zero plot, you can see the poles are more well within the unit circle compared to before, and that's indicated by that is expected with the fact that our filter is much weaker, so to speak. We only have 2 coefficients. So I'm going to reflash the board with these new coefficients using the bilinear transform, single order, and we should see some. Wow, much louder. That's right, because I had that turned up. Yep, and you can see here. Oh, no, this is wrong. This is all wrong. I didn't change the sampling frequency inside of Code Composer, so we're going to do that real quick. All right. There we go. That's better. That's what we expect. So if we look at this spectrum over here, this is the correct spectrum because we're not doing Gaussian noise or anything. And we can see that these frequencies below 100 are still making it through, and that's because our filter is much weaker. But the lowest frequencies aren't actually coming through, such as the ones around 20 hertz. It should be very deep bass, but they might not be there in the first place, I guess. Regardless, you can hear the filter is actually running. It isn't getting nans. I want to be sure that our filter is going to attenuate, though, like we would expect, which means that the filter is filtering like we expect. So I'm going to change these cutoff frequencies to be much more close together. 500 to 1,000. More attenuation means a stronger filter. This might break, and I'm betting it's because of this number right here. That's the litmus test for me right now. Is that value is greater than 1. Let's go ahead and look at the pole zero plot. Oh yeah, that looks great. I've done zooming. I've zoomed out of this just to see if I could find any poles, just like way out here, but no. Simulation again. Since we narrowed the bandwidth here, we get more attenuation at those lower frequencies. So I'm hoping to see that in real time here on the board. Okay, values have been updated. We are going to flash the board, the new coefficients. I'm gonna restart the song because it's about over. I think it broke. Yes, it did break. The y buffer is filled with plus infinity and plus infinity. And if I let it play some more, yeah, it's plus infinity in there. Not sure why it is positive infinity. Again, I think it's a rounding problem. Yeah, I'm going to leave that where it is. If for whatever reason I figure out why this is happening, I will change it. But if I didn't change it, if this is what you're seeing, then I wasn't able to figure it out. And I will take the L, as they say. Take the loss. Yep, because MATLAB doesn't mind. MATLAB doesn't blow up to infinity, but for some reason this DSP board does. And we can just look at the simulation function that I'm doing. We're generating the cosine signal here. This is the time duration. It's just 10 seconds at a frequency of f test, which before was 60 up in the actual outside of this function back in the main part of the program. Then we go ahead and fill the output buffer with zeros, set up our just an n vector or something, and then we're not using these anymore. Actually, those are gone. And then this outer for loop is simulating the getting new samples essentially. So we get a new sample, and then these are going to calculate the feed forward components that we get from the input values and the numerator vector coefficients. And so as j increases, so long as j is less than or equal to I, that way we don't. That way this doesn't end up being like x of 0, which MATLAB doesn't understand, or less than that. Then we just take the current sample value, which is given by this outer loop I. We take this current sample value minus some j value plus 1. So this minus j plus 1 will help us to, it'll help us, the plus 1 is necessary, because let's say we were calculating the current input sample. So the current input sample, like this B0 right here, has a related coefficient. And so if we're just starting, the current sample is 1, so we want this next part to evaluate to 0, because we don't want to go into the past yet. So j has to start out as 1 though, because it's in a for loop, and so I subtract 1 and then add 1 to bring it back to 0. Then as we iterate through this for loop, j gets bigger and we move further into the past samples inside the vector x. And then we do the same thing for the feedback. In this case, we're testing if j is less than I. If it's equal to I, we still get 0 here, so that's a problem. And then we're also only going from j equals 1 to essentially the length of the vector minus 1. And so since the length of a is 2, we go from 1, 1 to 1, if you want to call it that. So that means that in this case, we're just calculating the this coefficient here. We're not bothering with the current value and its coefficient because it's 1, and the current value isn't part of the filter necessarily. If that makes any sense, like the current sample is always delayed before it is then used in the filter. At least whenever we have derived this, that's what I understand. And so yeah, it does the same thing. It goes into the past as j increases and multiplies by the respective coefficient, and then stores the value, the current value, in y. So again, I is the current sample number, so the current output sample is going to be y of I. And then we just plot the stuff here. and it turns out like this. So let me show you something. We're going to do something within the passband. So something well within the passband. Let's look at our filter here. It looks like the best number is going to be like 700. 7,000. There we go. It's not going to be perfect, but it's going to be mostly there. Oh, what just happened? Oh, we just have a higher frequency. That's why this looks weird. We zoom in. You can see it isn't attenuating that much. We're from about 0.6-ish to negative 0.6-ish. So 1 to 0.6, that's, yeah, it's about 0.6 gain. And if I run ahead into my calculator and do (20 times log of 0.6), that's about negative 4 dB. So yeah, there. Pretty close. I might have been doing that wrong. I don't think so. Back up. Yeah. Yeah, that's good. So, with all that said, I think we're done with the RC filter demonstration. Again, if I do find out what was wrong, I will upload a different version of this video. But if I haven't, then it means I just couldn't. So that's that. All right, next after this we're gonna